Let's take everything we've learned about increasing, decreasing, concavity, inflection points, critical points, relative extrema, absolute extrema, and let's sketch the graph of a function using calculus. When we were in Algebra 2 and Pre-Cal, we didn't have as many resources available. Now that we've learned all of these things, we're going to sketch the graph of a function using calculus. Now, sketch just means what? It doesn't mean it has to be perfect, but it means that we're going to make it as accurate as we can. Let's go ahead and take a look at example 1. We have sketch the graph of f of x equals x to the fourth minus 12x cubed plus 48x squared minus 64x. So be considered a quartic function to the power of 4. And it's a polynomial. So, there's going to be a lot of steps here. We just focus on what's important, especially when it comes to graphs. There's some key things we need in order for the graph to be complete. Go ahead and take a look. First, we're going to find x-intercepts. Now, this is a quartic function. Normally, it's very hard to find the x-intercepts of a quartic, especially when factoring by grouping doesn't get what you need. In this case, factoring by grouping would not yield all x-intercepts. However, we can tell that an x can be pulled out of all 4 of these terms. I'm going to pull an x out, and now we're left with a cubic function. Again, you can't factor this by grouping. The question is, what do you do? Well, there's a little trick here. What we're going to do is move this minus 64 over with the x cubed. Now, why am I doing that? Because this is a difference of cubes. X cubed minus 64. Cube root of 64 is 4. And so I can use the difference of cubes formula. So here it is, down here. Difference of cubes is a minus b times a squared. Let's see, let me make sure I get this right. Yeah, a squared plus ab plus b squared. Okay, so plus 4x plus b squared, which is 16. Then we have the remaining minus 12x plus 48 left over. So now you're probably thinking, well, why do we do that? It doesn't seem factored. Well, focus down here at the minus 12x squared plus 48x. We can actually pull a GCF out of these two. Go ahead and do that. So we can pull a 12x out of both of those, or a minus 12x, and we'll be left with x minus 4. What do you notice now? Both of these have a x minus 4 in them. So you can pull that out as a GCF, even though it's a binomial. And when you pull it out, you're left with x squared plus 4x plus 16, the one factor attached to this, minus 12x, the other factor attached to the x minus 4. From that point, we can group the plus 4x and the minus 12x, and we'll make minus 8x. And now we're getting much closer to a factored form. Now this is a perfect square trinomial. If you were to use the x method, you'd have 16 on top, negative 8 on bottom, and 2 numbers that multiply to give you the top and add to give you the bottom are minus 4 and minus 4. And we can use the shortcut here because the leading coefficient is 1. So this factors into x minus 4 times x minus 4. And we had the original x minus 4 that we pulled out on top of the x minus 4 we just broke down. So now we have 3 x minus 4s and an x. Now this will come in handy later. If you notice, this actually will eventually factor into just x times x minus 4 cubed. Alright, but for now we're just going to set each of these factors equal to 0 to find our x-intercepts. The first factor will just be x equals 0. The next one we're going to get x equals 4. So there's a lot of work, but that just basically gives us 2 x-intercepts. Now, if you remember from pre-calc, this factor occurs 3 times. It has to do with multiplicity. Since it has an odd multiplicity, it will cross through the x-axis there. It will not, if it has an even multiplicity, it will touch but not cross. We'll see that later when we graph this function. Next, we're going to find the y-intercept. Now, since it's in terms of f of x, we'll call it the f of x-intercept. Remember, to find the y-intercept, just plug in 0 for x. Whatever you get is your y-intercept. I'm just going to plug this into the factored form already. So x times x minus 4 cubed. It's the same thing as the original function. And we get 0, 0. So 0, 0 will be our y-intercept. And once again, we have an x-intercept at 0 and 1 at 4. Okay? So first two steps, always find your x and y intercepts. That way you know where it touches the x and y axis. Next, you're going to check for asymptotes. This is going to be true for rational functions and even exponential and logarithmic and trigonometric. But for a polynomial, it has no asymptotes. So for step 3, you can just move on to the next step for any polynomial. Now we're going to reach back and use some calculus we learned. We're going to figure out where the function's increasing and decreasing. So fortunately, we've already factored this function, right? And that's important for increasing, decreasing, because you want to figure out the critical values. When we do find increasing, decreasing, we have to take the derivative first. The derivative of this is going to be using the power rule, 4x cubed minus 36x squared plus 96x minus 64. From there, we would pull a 4 out because all of these are multiples of 4. We hit a roadblock with x cubed minus 9x squared plus 24x minus 16. So since we can't really figure out those critical values, we're going to use the factored form of our function to figure out where it's increasing and decreasing. So we will be using the x times x minus 4 cubed that we used to take the derivative. That way we can find those critical values for the derivative. This will be the product rule, a prime b plus ab prime. So here's my ax, and my b is x minus 4 cubed. We're just going to find the derivative of both of those. We can see derivative of this is going to be 1. This will be 3 times x minus 4 squared. So there's my a prime, there's my b prime, and then the product rule is a prime b plus ab prime. It's going to be 1 times x minus 4 cubed plus x times 3 x minus 4 squared. We're going to simplify this. This will be 3x. And then notice something. We can actually pull out an x minus 4 squared because they both have an x minus 4 squared in common. So we'll be pulling that out as a GCF. And we will be left with an x minus 4, because this is a power of 3, plus 3x. Okay, and we are setting that equal to 0 to figure out what the critical values are. So we've got basically two factors now. Now this x plus 3x is going to become 4x. So it'll be 4x minus 4 times x minus 4 squared. Okay, so for our first factor, we're just going to get x equals 4, right? When you set this equal to 0 and solve. So there is our first critical value. The second one, we'll set 4x minus 4 equal to 0, this factor equal to 0. And kind of notate that here so you can see what we're doing. We're going to solve for x, and we're going to get x equals 1. So a second critical value is x equals 1. Okay, so this is kind of a tricky problem. We had to see how to factor this so that we could take the derivative and find the critical values. So x equals 1 and x equals 4. All right, now we're going to go to our chart, which involves increasing, decreasing. We know from before that we're going to have 3 intervals with 2 critical values. First interval, negative infinity to 1. Second one is 1 to 4. Third one is 4 to infinity. So test value between here would be 0. We're going to plug that into the derivative. We're going to get negative 64 back. This tells us that on this interval it will be decreasing since we got a negative number back. Between 1 and 4, we're going to plug in 2. We're going to get positive 16 back, so it's going to be increasing on this interval 1 to 4. And from 4 to infinity, we're going to plug in 5. We're also going to get positive 16 back, which is kind of weird. But at any rate, that's a positive number. So even from 4 to infinity, it's going to continue to increase. You can see here that there's no change in direction, so there will be no relative min or max here. There will be a possible one from here to there since it goes from decreasing to increasing. So we'll add our extrema column, and there will be a possible one at x equals 1 since it changes direction there. When we plug in 1 into the original, remember we have to plug that back into the original, we do get a value back of negative 27. So that means there is a relative minimum at 1, negative 27 since it went from decreasing to increasing. Okay, what's next for our next step? Well, after step 5 of finding relative extrema, step 6 is going to be to determine concavity, which means finding the second derivative. Now, for this one, we can just use our original derivative of the original function without the factored form. So we're going to take the derivative of that again and get 12x squared minus 72x plus 96. Just to refresh your memory, this is what the original function was. This is one possible derivative, the one where we didn't take the derivative of the factored form. We're taking the derivative of that again. And getting 12x squared minus 72x plus 96. Now we can notice the second derivative exists for all x, so we just have to figure out where it equals 0. Set this equal to 0, pull a 12 out. We can use the x method here. The top would be 8, the bottom would be minus 6. On the sides would be minus 4 and minus 2, which is what's going to become our factored form. We have two critical values here, x equals 4 and x equals 2. And set this equal to 0. The 12 won't matter because it never equals 0. Now we're going to do our chart for concavity. Remember, we're plugging these test values into our second derivative. Since we have two critical values for second derivative, we'll have three intervals from negative infinity to 2, 2 to 4, and 4 to infinity. So right here. First test value is 0. We're plugging that into the second derivative. We get a positive number back, so it's going to be concave up on that interval. Second interval is from 2 to 4. We can plug in 3 into the second derivative. We get negative 12 back, which means it's going to be concave down on that interval. Next, we're going to plug in 5 into the second derivative for the interval 4 to infinity. We get positive number back, so it's going to be concave up on that interval. We can see some change in concavity here, so we need to check for inflection points by making an additional column to check for inflection points at 2 and 4. So that's where our possible points of inflection will be for step 7. We want to figure out where these inflection points are, but we have to plug these back into the original to see if indeed we get a point back. Plug 2 back into the original, we do get negative 16 back, so we know we have a point of inflection there at 2, negative 16. And we plug in 4 back, indeed we also get a number back 0, so we have another inflection point at 4, 0. Okay, what's our next step? Now we're going to, for step 8, plot and label points in asymptotes. So let's talk about each of these points. First, we found an x and y intercept, both at 0, 0. We also actually found an x-intercept at 4, 0, which also happens to be an inflection point. So it can be both. It's the same point, so we only need to label it once. We found an inflection point at 2, negative 16, right here. Okay, and again, that's also an inflection point. If you want to label these, you could just use like IP for short for inflection point. And over here, at 1, let me make sure I get this point right, negative 27, we have a relative minimum. So you could just maybe label this as a min. Okay, now it's important you label these because when you go to connect the dots, you want to know what each point is. Since I know this is a relative minimum, I know the graph is going to go from decreasing to increasing. Since I know this is an inflection point, I know the concavity is going to change right there. Also right here, the concavity will change. So I'll just label this as an inflection point as well. So you're just basically going through and plotting all these points that we figured out from the previous steps. Okay. So let's go back to the graph. Now the next step, for step 9, we're going to plot figure out additional points. Well, 0, 0 is not an additional point. I'm not sure why I did that. I guess if you do need additional points and you haven't found one at 0 yet, that's a good place to start. But since we already figured it out for the y-intercept, again, I'm not sure why I did that. But I do know why I did 5. So you want to pick a point somewhere to the right of your last point, if that makes sense. So since our last point's at x equals 4, I just plugged in 5 just to kind of see what's going on here. Another point I might recommend is like plugging in negative 1, so a point to the left of 0. So actually I'm going to do that, even though I didn't do it before. Give me 1 second. We'll plug in negative 1 to the left of here and see what we get back. So when we plug in negative 1, we actually get 125 back. So what that's going to tell me for my additional point is that it's going to be way up here somewhere. Okay, this is going to help me connect the dots. Okay, and so at 5 we got 5. Again, it's kind of going to tell me what the ends look like to the left or right of my graph after I've already plotted my inflection points and my relative min and max, x-intercepts and y-intercepts. So just plot those values on the left and right, see what's going on with the graph. Okay, so now we're going to kind of sum up all of our intervals. We know it's increasing from 1 to 4 and from 4 to infinity. We know it's decreasing from negative infinity to 1. And so going back to connecting these dots, if it's increasing from 1 to 4, I know I'm going to have to be going up. It kind of makes sense the way the points are. If it's increasing from 4 to infinity, I can keep going up past 4, but I know there's an inflection point here, so I'm just going to have to make it go from concave down to concave up. And then for concavity, you kind of you're sketching one curve, so you want to kind of keep that in mind as you're connecting the dots. Concave up from negative infinity to 2 means that it's going to be U-shaped, okay? And then from 2 to 4, we can see it's going to be more opposite U, maybe not quite as dramatic, but in other words, maybe go like this where the water runs off, and then it's going to change concavity again at 4, and it's going to go back to concave up, so we'll go back to more of a U shape. So now it's time to connect the dots. Let's take a look. So here we have all of our points. We're going to go ahead and just draw our function, understanding where the concavity intervals are, increasing, decreasing, and additional points. Alright, so there we have it. Here are all the different lines connecting. I want to go over this one more time just to make sure we understand how to connect these points and how to use concavity and increasing and decreasing. We can see right off the bat that point we plugged in negative 1, 125 is going to be way up here. We know it's decreasing when we start out. We know it's concave up, so we can kind of make it more of a U shape. Okay, and we're going to keep going down to 1, negative 27, which is where the relative min is. So at that point, we know we have to start going back up. Then at 2, negative, I think it was 16, we had an inflection point. So what happens there is, you can see the graph goes from concave up to concave down. So you kind of have to bend it a different way, right? Until you get to the next inflection point at 4, 0, which is also an x-intercept. In case you didn't notice, 0 right here, this is actually our x-axis. We're just making sure we can see the entire graph. But at this point, it changes back to concave up. So you want to trace more of a U shape. And going through your additional point here at 5, negative 5, and then going up, concave up on both sides. And, I do recommend drawing arrows on the left and right of your graph. Just indicate that it increases on the left. So that's it for all of this information, using it all to sketch the graph of a function. If you have any other questions about this example, let me know.